We are going to talk about differentiating what are called implicit functions. So everything you've worked with so far has been an explicit function, which is like y equals. An implicit function is a function that's not solved for y. Sometimes it's just not solved for y, and sometimes it's entirely not possible to solve it for y. And then you have to use this technique that we're going to learn called implicit differentiation. What we're going to do is we will differentiate both sides with respect to x, which means just like you're used to, x is your independent variable, and when you take its derivative is just 1. In our second notation that we haven't used much, it looks like dx over dx, the derivative of x with respect to itself, which that kind of makes sense that is just equal to 1. When we're differentiating y with respect to x, when we do our derivative y prime, we're going to write it as dy dx, or the derivative of y with respect to x. It's a little bit less messy to work with than y prime. So let's try one. We're going to use implicit differentiation to find this derivative. So now we have to use the product rule because we have a function that has taken one of our variables x times the other one y. So I'm going to set it up first, x times derivative of y plus derivative of x times y minus 0. Derivative of the other side is also 0. So I'm going to go ahead and take my derivatives and write y prime as the derivative of y with respect to x. Derivative of x with respect to itself is just 1. And then we're going to go ahead and solve this equation for derivative of y with respect to x, dy dx. So I'm going to work to get that by itself, just like I would in a normal equation. So subtract y, and then divide both sides by x. And you end up with the derivative of our function is dy dx equals negative y over x, which is a little different than normal because it has two variables in your derivative. Essentially what that means is if I wanted like the slope of my tangent line to my function at a point, I'd have to plug both the x value and the y value of that point in to get my slope there. In this case, there was another option. This function I could have rearranged and solved it for y pretty easily. So let's do that and compare. So I could add 3 to both sides, divide by x, and then just to make my derivative easier, write it as 3x to the negative first. So taking my derivative, I'm going to get negative 3 over x squared, which looks different than what I got for my derivative using implicit differentiation, but really, those two things should be equivalent. So let me show you that they actually are. So when I did my derivative with implicit differentiation, I got negative y over x. So up above, when I solved for y, I had y is equal to 3 over x. So if I go to my implicit derivative and plug in what I got for y, so my 3 over x, and then simplify. So I'm just going to make that negative 3 over x, and then I'm going to have to multiply by my reciprocal, so multiply by 1 over x. That gets me negative 3 over x squared, which is the exact same thing as what I had when I solved for y and rearranged it. So let's try another one. If I take the derivative of this implicit function, I'm going to start with the derivative of 2x squared, which is just going to be 2 times 2x to the first. If I take the derivative of my second term of 2y squared, now this is our dependent variable, so I'm going to have to do my coefficient of 2 times 2y, and then actually the derivative of y itself. That's going to be equal to derivative of 4 is 0. Now let me talk for a second about what I just did there with the y squared. So if you think about kind of chain rule, the derivative of y to the second power, if you think about bringing the exponent down and multiplying by it, leaving the inside the same, and decreasing the exponent to 1, you still have to multiply by the derivative of the inside, which we don't exactly know. We just are saying it's whatever the derivative of y with respect to x is. So that's why we need that dy dx in there. And that's kind of like versus our derivative of x squared that we just had. If we think about that the same way, bring your exponent down, leave the inside the same, decrease your exponent to 1, And then the derivative of the inside is the derivative with x with respect to itself, which that's just equal to 1. So if you're taking the derivative of y, make sure that you have dy dx. Back to simplifying and solving. So we're going to have 4x plus 4y times dy dx equals 0. And then again, I'm going to have to rearrange and solve this function for dy dx. So subtract your 4x from both sides and then divide by 4y. And you're going to end up with negative 4x over 4y, which you can simplify by dividing out a factor of 4. Just get negative x over y. Okay, so we're going to stick with that same relation, and we're going to find the equation of our tangent line to this relation at the point 1, negative 1. So I went ahead and pasted my derivative in here because I'm going to need that to find the slope of my tangent line. So if I start with y equals mx plus b, let's go ahead and find that slope. So whenever I'm finding my slope here, it does require both my x-coordinate and my y-coordinate when I plug it into my derivative. I just end up with positive 1 for my slope. And then taking and plugging in my x and my y-coordinates along with that slope, I'm going to have negative 1 equals 1 times 1 plus b, which is just going to get me a y-intercept of negative 2. So my tangent line is y equals x minus 2. Now I'm supposed to graph this function and my tangent line on the same graph. So let's do a quick little refresher. This is a circle. Circles equations are x squared plus y squared equals your radius squared. So I'm going to divide my equation by 2 so that it is actually like you can tell what its radius is. Its radius is square root of 2. Okay, so I changed my scale on my graph a little bit here because square root of 2 is like 1.4 something. So let me put my circle in. And then if I draw my tangent line, it should be tangent at the point 1, negative 1. And my slope is just 1 here, so plots points. And then, yeah, it looks like my derivative and my function are matching up. My equation did give me the line that's tangent at 1, negative 1. Okay, something I want to point out here is the reason it requires both an x and a y value for our derivative is that I have 2 points that have an x value of 1 on this relation because it's not a function. One of them looks like my tangent line would have a slope of negative 1, and the other one has a slope of positive 1. So the x value alone is not enough to tell you what the slope of the tangent line is. You need that y-coordinate as well. First off, apologies if you can hear my cat purring because she seems really loud on my lap. But we're going to find the derivative of this function. And it's got your favorite exponential functions and trig functions. We are going to have to use the product rule. So I left my e to the y by itself, and then derivative of tangent is secant squared of x. And then my second half of the product rule, derivative of e to the y is my original exponential function times the derivative of the exponent, and then times tangent of x. That equals derivative of the right-hand side is 2 plus 3 times derivative of y with respect to x. So to actually solve this for dy dx, my terms that have what I'm trying to solve for are on different sides of my equation. So I need to actually rearrange this equation. So I'm going to get everything with the dy dx on the right-hand side of my equation and everything that doesn't have one on the left. So just quick little subtracting 2 from both sides, subtracting my e to the y times dy dx times tangent x. And the reason I did that is so now I can factor a dy dx out of both the terms on the right. And then that's going to leave me with 3 minus e to the y times tangent of x. And my left-hand side of my equation is still the same, so copy paste. If I'm trying to solve that for dy dx, I'm multiplying those two things together. So I'm going to divide both sides by the whole quantity, 3 minus e to the y times tangent of x. And that's really what the derivative of y with respect to x is equal to. One note, if you moved things to the opposite side of your equation when you rearranged it, your answer might seem wrong, but really if just both of your signs are backward, it's equivalent and it's totally fine.